So another common problem with your predictor variables is something called collinearity. Collinearity is just a fancy word that means the predictor variables are linearly dependent, or nearly linearly dependent. That is, one or more of the predictor variables can be thought of as a function of the others. For example, if you have a data set that includes a bunch of physical attribute measurements on people, like height, weight, age, sex, race, etc. Maybe you have 2 or 3 predictor variables that more or less tell you the same information. For example, maybe you measure the lengths of their femurs, and you measure their heights and the lengths of their ulnas in their arm. It seems pretty obvious that these 3 variables should be strongly positively correlated, and so in fact, you probably only need one. So on one hand, this presents an issue when you go to collect the data, because it's a lot more work to make 3 measurements on everybody than it is to make 1 measurement on everybody. On the other hand, this can also lead to computational difficulties when you go to do least squares and build a regression model. So remember, X here is your model matrix. It's your model matrix. Each column contains the observations on a particular variable, and typically the first column is a column of 1s for the bias term, right? Remember, when you do least squares, our beta hat vector turns out, remember, the solution to that is x transpose x, quantity inverse, x transpose y, right? So obtaining these estimates for the true betas requires us to invert this matrix, okay, the x transpose x matrix. X transpose x will be singular, it's another way to say that, or non-invertible, same thing, if there exists linear dependence of these predictor variables. So got a little simulation I'm going to do here. I'm going to get some uniform pseudo-random numbers between 20 and 60. I'm going to get 100 of them, and that'll be my predictor variable number 1. I'm going to take predictor variable number 2 here, x2, to be a perfect linear combination of those things. So you can think of maybe x1 is height, and x2 is 8 plus 2.5 times height, or something like that. It should be obvious that in this case, if we were actually doing statistics and x1 contain data and x2 contain data, then you really only need to collect observations on one of these variables and not the other one, because there's a perfect mathematical functional relationship between the 2 variables described by this right here. Now, perhaps you have this response variable, y, and I don't know what this is, maybe IQ or age, blood pressure, I don't know, some other thing that you'd like to predict. And again, I'm making up these data just so that we can see what collinearity might look like in a picture. I'm going to set it to be purely just a function of x1 here, because hey, you know what, if I could also put x2 in here, but I don't need to, because I know that x1 and x2 are linearly dependent. And then I'm going to add some error to it. Oops, this is a little typo. This should actually be 100, right? Because I need an error term for each one of these guys. I'm going to get 100 little random errors from normal distributions with mean 0 and standard deviation 23. I'm going to get a column of 1s here, and there's another typo. I think that should be 100 of them, right? And then my model matrix, you'll see, is going to be 3 columns. It's going to be this column of 1s, right, for my bias term, remember, and then my x1 values down here, and my x2 values in the 3rd column there. Let's go over to RStudio and take a look. Yeah, need to correct that, I guess. So let me just run these first few lines of code here. I've told it to spit out my model matrix there. That's what the parentheses do here. When you put parentheses around something, it'll actually display that. It'll print it out. Okay, so X, that's my model matrix. And so if I go to invert that matrix, and by the way, that's what the solve command does here. That's what the solve command does in R, is it inverts whatever's in the parenthesis there. You get an error message. It says a system is computationally singular. That's what that means. It's non-invertible. The matrix is ill-conditioned. Let's take a look at a graph, if we can, and see if we can make sense of what's going on here. I'm going to use that RGL package so that I can make 3D plots. And it's really handy because I can rotate them around and stuff. So you can see that, let's see, x1 and x2, those are my predictors down along the bottom. My response is in the up-down direction there. You can see what is going on. All those points lie in the same vertical plane. That's not what we want to do. Remember, folks, what you want to do is you want to be able to try to model the response, y here, with a function of the other 2 predictor variables. In that case, it'd be a plane or some other kind of surface that doesn't go straight up and down like that, right? Because that's not a function, at least not in the traditional sense. It fails the so-called vertical line test, right? Ideally, what you want, if you were going to make a a regression model here is, some sort of a plane or some kind of a surface that, say, sort of cuts through this way, cuts through there, okay? But it's impossible to do that because we have no information to the left or right of this sort of vertical slice here. There's an infinite number of sort of best planes, right? The best I can do if I wanted to model this point pattern is to use a straight up and down plane, which again I don't want to do because I want to model the predictor there as a function of these variables, or I could draw a straight line sort of right through that point pattern, just a one-dimensional thing. If I was going to come up with two-dimensional models, there's really an infinite number of planes that would sort of slice right through that line. We can draw a few of them here with R. Here's one plane. Let me show you here. Okay, there's one plane. You can see, like I said, it sort of goes right. It slices right down through that line. But I can get another one, right? Now there are a couple of planes. Both of them are running right through the line there. Okay, and I can look at it on this angle. You see that they intersect right there, right along that sort of along that one-dimensional line. Okay, I can get another plane. Okay, now you can really see the problem there, right? All three of those planes model the response using those two predictors just as well as each other. None of them are better, okay? The problem is we don't have any data taken off to the right over here or off to the left over here. They're all up and down above or below each other, okay? We need to collect data. If I'd taken even just one data point over in here, then suddenly that would give me more information to really inform a better planar model that could help describe the response in terms of these two variables. But the problem here is that x2 is an exact linear function of x1 and vice versa. So really I only need information on exactly one of those variables. So all that's really needed here is that, I'll just do this down in the console here. You see that all I really need to do is look at y versus, say, either one of those guys, y versus x1. You'll see it looks like this. Then I could drop a regression line onto it, like so. And that's really all that's needed. What I have over here is essentially, if I'd included another variable, this other dimension, x2, see that? But really, what I've got going on here, if you sort of squish that x2 dimension like that, this is the random point pattern that you see here. And this is really all that's needed. Now, this is a very contrived and sort of pathological case. In practice, you'll very rarely see exact collinearity. That's what this is, exact collinearity. In real life, when you're doing statistics and you're building these regression models, you're much more likely to see sort of near linear dependence, where your predictor variables are highly correlated, but not exactly so. That's another thing too, right? If I look at the correlation between x1 and x2, it's going to be exactly +1, right? Okay, so that's the idea there. So there can still be computational issues if the columns are slightly linearly dependent. What I'm going to do is I'm going to go back to my model matrix and I'll go back to, say, 80th row, third column, where the x2 value is there in the 80th row, and I'm going to perturb it by 1 part in 10,000. And then I'll go and try to invert that x transpose x matrix. I'm going to run that, and I get the same error message. This matrix is no longer singular, but computationally it might as well be, because these two variables are so nearly linearly dependent that R is unable to invert x transpose x. If x transpose x is almost singular, that is almost non-invertible, again, you're likely to encounter computational problems in getting its inverse, and also even then it's still likely that you really don't need to collect information on several of the variables. Maybe you only need to collect information on a subset of the variables. But this is called collinearity or multi-collinearity. The situation can give really inaccurate regression coefficient estimates, meaning the standard errors can be very high. And you can see why that is if you look back at this picture. You might imagine, even if our data points didn't lie in this perfect up-down vertical plane, that if there was some spread to them, slight spread to the left or right, that they would constitute a random sample from a larger group. And when you actually go and get a regression plane, that regression plane may be very, very steep and pitched this way, okay? Might be sort of pitched up that way. Then, if I went and took another sample of the same size from the same population, it may be that my new regression surface is pitched the opposite way, also very high, but now one or more of those model coefficients might have changed sign. So the standard errors can be high or inflated. So let's take a look at this next chunk of code. I'm going to perturb my x2 values now. I'm going to get some new x1 values. I'm setting the seed at 59. X1 values here. My x2 values are going to be, again, essentially a linear combination of the x1 values, but I'm going to perturb them each by a little bit more this time and take a look at what happens there. You see the same sort of picture that we saw before, but if I look at it straight on this way, I see that these points do not, in fact, actually sit exactly on a vertical plane. Again, like I was describing before, if I went to try to model y, my up-down response variable there, is a function of x1 and x2, these two predictor variables, the plane might slice off sort of more this way, or it might slice off more sort of in that direction there. Okay, it can be very different. So the collinearity is really easy to see in this example because there are only two predictor variables, and the situation is really pretty extreme. In real life, especially when you have more than 3 predictor variables, the collinearity can be much more difficult to detect with your eyeball. So we rely on several other ways. First way, one thing that a lot of people do is to check for pairwise correlations. Okay, they'll get the correlation matrix just for the predictor variables. However, you got to be careful here. Don't rely on this test alone because it can be faulty. It can be misleading. When in this case, again, we don't just call it pairwise correlation detection here. The issue is something called multi collinearity, meaning that 2 or more of your predictor variables could be highly correlated. It could be that 2 or 3 predictor variables are very useful in describing one of the predictor variables. So just checking these pairwise correlations may fail to actually detect or alert you when multicollinearity is actually there. But still, people do this, and certainly if you see a high correlation between predictors, then that could certainly be evidence of collinearity. If you see a correlation value of 95% or negative 95%. Second, if the addition or removal of a predictor variable significantly impacts the magnitude of the other variables, collinearity might be present. Number 3, suppose that there are some predictor variables that based on experience, should be included in your model. And so therefore those corresponding model parameters should not be deemed insignificant and thrown out. Well, for those predictor variables, if you're getting wide confidence intervals or large standard errors for those corresponding model parameters, that could indicate collinearity. Number 4, if when you go to regress the response onto a set of predictors and it shows predictor I to be insignificantly different from 0, and by predictor I really mean what the model coefficient is if the p-value is not small in your standard R output there. But when you go to regress the response onto predictor I only, when you just make a basic linear model that regressing the response just onto predictor I, and that finds predictor I to differ significantly from 0, this can be a sign of collinearity, right? If you think about that, I think that makes a lot of sense. Essentially, predictor I seems to be significant, and then suddenly it doesn't when you include some other variables. Number 5, suppose you go to regress predictor I onto all the other predictors, okay? So forget about the response, throw it out. We're just looking at the relationships between the predictor variables. So pick the ith predictor and regress it onto the other predictor variables. And if that gives you a large R squared value, maybe you call it Ri squared, and this indicates predictor I might be very, pretty well described by some linear combination of the other predictors. So do this for all the predictor variables and look at all the Ri squared values. Then the predictors that may be the culprits here, maybe they can sort of be discovered. You can sort of take a look at the coefficients for the regressions with the large R squared values. Number 6, calculate condition numbers. Okay, obtain the eigenvalues of x transpose x, where again, x is the model matrix except without the first column for the bias or intercept. Okay, or perhaps even better, calculate the condition numbers for the covariance matrix or the correlation matrix and get the eigenvalues of that guy. I think a lot of times that's even really the better approach. You want to center your data first. That's what you get when when you look at the covariance matrix or the correlation matrix. Get the eigenvalues of those things and rank them in order from highest to lowest. We'll see this kind of thing again when we study principal components analysis and principal components regression. But it turns out that the eigenvectors of the covariance and correlation matrices point in orthogonal or perpendicular directions through your predictor set, through your predictor space of the most variance. And the eigenvalues are the variances along those so-called principal components. So a high eigenvalue, for example, if lambda 1 is high, what that means is that there essentially is a direction through your predictor space that captures a large amount of the variation in your data. So the condition number, maybe there are actually several of them, but if you look at the square root of lambda 1 over lambda p, what this is essentially, that lambda 1 is the largest eigenvalue, lambda p is the smallest. Each one of these things is really a variance along a certain direction. So if I take the square root of this stuff, it's a ratio of standard deviations. Okay, it's sort of the ratio of the largest standard deviation to the smallest. If the condition number is relatively large, then it indicates that collinearity might actually exist there. You can also compute other condition numbers, like take the largest over each successive one and take the square roots. Values over 15 indicate a collinearity concern, and values over 30 indicate possibly a major concern. These are just rules of thumb, therefore they're really only as good as your thumb. Finally, number 7, something called the variance inflation factor. So recall that the variance for the j'th model coefficient is given by this. We saw that earlier in the course, where sigma squared is your common error variance, rj squared is this guy up here. It's the r squared value when you go to regress the j'th predictor onto all the other predictors, and then times 1 over the sum squared deviations about the mean for predictor j. This part, just this number right here, this is called the variance inflation factor. You can see what happens if rj squared is high. We know from our previous discussion up there in number 5 that a large rj squared value can be a sign of multicollinearity, right? So look at what happens there. If rj squared is high, then the denominator here is going to be small, and so this entire factor right here, 1 over all that stuff, is going to be large, and therefore the variance estimate for our j'th model coefficient will be inflated. It'll be high. This is what leads to your standard errors being too large and your confidence intervals for your betas being too large. Variance inflation factors, or VIFs, in excess of, say, 5 or 10. Again, this is also just a rule of thumb, but this will indicate possible presence of multicollinearity. Next, we'll take a look at an example.